Okay, so I'm recording the class because Margaret's not here. So say hello to Margaret. Okay. she asked. She, she asked me to record the class. Anyway, what we did the other day was we looked at the force on a moving charge, and the force was equal to the speed of the charge times the amount of charge on the charge times the strength of the magnetic field times some angle, so say some function of the angle. So normally we're looking at the simple case where the magnetic field and the velocity vectors are perpendicular to each other. And as a consequence, the force vector is perpendicular. Well, in any case, the force vector is going to be perpendicular to the velocity and the magnetic field vectors. And that's actually how they define the magnetic field strength. It's the force that a charge would feel moving at a certain speed. Now the question is, I mean, you could, like an electron, you know what the charge on an electron is, or if it's an ion of some kind, you probably can figure out what the charge is. And then if you can figure out what the velocity is of that charge, then you could shoot this known charge at a known speed. You could measure how the charge moves using Newton's second law to figure out what the force is, and then you could calculate the strength of the magnetic field. So you can solve this one. And these are assuming that everything's perpendicular to each other. Because a wire is just a bunch of charges moving in a common direction determined by or common bulk direction determined by the wire, the force on a current carrying wire is equal to the current times what else is there? The magnetic field strength times the length. So it's just taking each individual charge that's in the current and summing all those up to relate that to the current. We saw that the torque on a current carrying loop was equal to the current times the magnetic field strength times the area. And that kind of makes sense because, you know, if this ends up being newtons, and here I'm multiplying by length, if I multiply by area, I've got an extra length unit in there, so it's going to be newtons meters, or meters newtons, which is a torque. So from a unit perspective, it makes sense that works out. And I, you know, we were looking at this the other day. Was you know, here's my current carrying loop, and you know, this is say the x dimension, and this is the y dimension. So the area is just x times y. But it turns out that this dimension contributes to the force. So that's related to force, whereas this dimension here, the y dimension, is related to the torque arm. You know, we've got this force acting at this distance. So that force times distance gives you torque. But when you combine these two together, it turns out it's just the area. And, you know, if you have a loop that looks like this, purposely making it weird shaped. I'm not that bad a drawer. But if you ran a current through this wire, it still would work out. If you use the area, so you'd use the cross-sectional area, however you figure that out. In this case, it's easy. It's just these two multiplied together. Here, it's some unusual shape. It still works, surprisingly, but it does. Okay, so then we looked at, we said if you have a current carrying wire, so this is a wire that has a current going through it, that you have magnetic field lines going around the wire like this. The direction's dependent upon a rule, right-hand rule, and it says the magnetic field strength is equal to mu 0 times I divided by 2 pi times the distance from the current. Mu0 is another constant, like epsilon 0. Has a name which I always forget which one's which, so I'd have to look it up. But I is current. Let me see if I can find a video showing you how this works. An experiment. And I'm trying to remember the guy's name who did this. I might have to look it up in the book. It's a Dutch guy, which is, his name is probably, what's Dutch names? Van something? Or I have some Dutch person in my family tree. I don't think it was somebody who married into, his name was Van der Plant, yes. So Van, a lot of Dutch have a prefix Van, Vander Sladen, or Vander, what I don't even know where that came from, but make up names with the Van in them. So let me think about this. Magnetic field around a current carrying loop, around a wire. Magnetic field, okay. So it's approximately in this area of the book. And force between parallel conductors, magnetic field. What was the guy's name? Well, I'll just search for magnetic field around video. Video, magnetic field around current carrying wire. There you go. First we gotta watch Goldilocks for a few seconds. Okay. Oh, it's Khan Academy video. So what he's got is just a 6-volt battery and a wire, and apparently he's got it connected. I don't know how oh, there he is. It's like he hasn't connected it to ground yet. So what he's got is a compass near the wire, and I guess he's turning it on and off. So that wasn't exactly, well, maybe this one will show. Yeah, this looks like a good one. If that's a preview. The high school physics project, okay? Magnetic field around a current carrying wire. Let's see what he's got. Oh, that doesn't look like what I'm looking for. Okay, so let me explain. I'll just describe it. Can't always find what you're looking for. Let me stop this thing. So what this guy did, which I can't remember his name, it'll come to me. Subconscious will work on it. So he was the Dutch guy, and he had a wire with current running through it, and I don't know why he had compasses around it, but what he found out was that the compass, the direction of the compass would follow. If you went around in a circle, it would be always tangent to that circle. So let me just draw a compass here and put it into around my wire. So here's my compass, and you've got, the north and south pole, so it's pointing to the north pole there. And what he would find out is that if he brought it inside near this wire, that these arrows would be going that direction, and if you have one, so we'll do another compass that goes this way, and one that goes that way, and one that goes down. So these are all the compasses, and they're not fixed. Of course, they had to get stuck together, didn't they? Okay, let's try it again. So let's do one that's up over here. Okay, and deactivated. So I need one that goes the other way here. Okay, so there's another. So if you put a compass up here, it would go that direction. and I've got this one in the wrong direction, so it's not going to do me any good. It needs to be going down. So here's another compass, and if he put the compass in the presence of, group those together. If he put the compass over here, it would go down, or he put multiple compasses and then he put one there. And so they would see that. And if you turn the electricity off, then they would all point to magnetic north. They'd all point in the same direction. Then you turn the current on and they go, boom. They would, follow. And it didn't matter where you put it. Of course, I'm not sure how he would have measured the strength of the magnetic field, but he knew the direction that it goes around. If you put iron filings like you would normally use to visualize the magnetic field around a bar magnet, if you did the same thing, took a piece of paper, had the wire sticking through like this, put some wire filings on it, and set the current flowing through the wire, they would all align up in circles. The interesting thing is there's no poles on this. There's no, like a normal magnet, you have a north pole and the south pole. You don't really have a pole. All you have is that the magnet, the compass is going to line itself in a certain direction. It's going to be pointing this way to the north, but if you went over here, there's no north pole that's sitting over here to point to. Okay, so the next thing, so how did they figure this out, this equation? So there's this thing called Ampere's law, and obviously it was developed by Senor Ampere. Actually, I think he was French. Monsieur Ampere. And if we mentioned this briefly back when we were talking about electric fields. There was Gauss's law, and Gauss's law said that the electrical flux was equal to the charge divided by epsilon 0. Okay, so there's that epsilon 0 showing up. And we used that to look at the electric field around a circular, like a sphere, for the special case of a sphere, because it's hard to use Gauss's law. And remember, this is actually an integral. So you're integrating the electric flux over a surface area, kind of like we did in section 4 in calculus. We calculated surface areas, so that's what we're talking about. And Q is the charge inside the sphere, so that's so many coulombs. Epsilon 0 we know is 8.85 times 10 to the minus 12 something units. And so if you sum up all those electric fluxes, it's equal to the charge inside the sphere divided by this. Okay, so there's a similar one for magnetic fields, and what it says is Ampere's law, and what it says is that it's called the line integral. Okay, so it's an integral sign with a little circular loop on it with an arrow of the magnetic field vector dotted with this little dl vector. I'll explain this in a second. And that's equal to mu0 times I, and that's it, I think. Let me make sure I got that right. So I'm pretty sure they do have Ampere's law in the back here. Ampere's law, 933. Okay. So Ampere's law is that the integral of the line integral of the magnetic field vector dotted with the dl vector is equal to what? It just says. Okay, so I did do it right. Yep. Yeah, it is mu0 time. Yep, mu0 time. So I have it right. So mu0 again is this constant, and that's actually how they you can use Ampere's law for this special case, and it's a special case because the lines are circular, and also the magnetic field vectors are always in the same direction as the dl vector. So let me kind of try to explain what this is. We're not going to actually develop it, but just kind of give you an idea how that works. So for our particular case, we have this current wire that has current. And because of the symmetric nature of the magnetic, the symmetric nature of this whole thing, what we do is we take a circle, and then this part is dl. And then you have the magnetic field vector, which turns out to be exactly in the same direction as dl. So that's the magnetic field vector at this point. So that's a vector. And this little dl also has a direction, so it's a vector as well. And when you do the dot product of two vectors that are in the same direction, it just ends up being the product. So what we can say is if the magnetic field vector and the dl vector are in the same direction, then B dot dl just equals B, the magnitude of B times the length of dl. So you lose the vector. You don't have to. It's an easy dot product. And then if you are actually, we are going to derive this thing. So then what you can do is you can say, well, because of the symmetric nature of the wire is round and the circle is round, that B should be constant at any point at any given radius. So when I do the integral, because B is constant and the dot product just says I multiply stuff together, my integral here, the line integral of the B vector dot the dl vector just becomes equal to B, the magnitude of B, times the integral of dl. And how far if you go around a circle, what is the total distance that you travel around a circle? It's the circumference. So it's going to be equal to, so dl integrated around the circle is just 2 pi times r. And so Ampere's law says that, therefore, that for this particular case, the strength of the magnetic field at some distance is going to be times 2 pi r is going to be equal to mu 0 times I. And if you solve for the strength of the magnetic field at a particular radius, it's going to be mu 0 times I over 2 pi r, which is exactly what the formula is. So that's how they got that. Okay. So I'm going to run over and get two things out of the other. I forgot to bring them over here, so you can take a 2-minute break here. Okay, back. So the next thing we're looking at is this scenario. We're going to do this in lab next week. We're going to look at these different situations. Did I turn that thing off like twice? Yeah. Okay, so I don't hear anything. Maybe I turned it off. Let's try it again here. Oh, there we go. Okay. So what this is just some wires, kind of like we had wrapped around the motor. It's actually how many turns? So there's 200 turns. What we're going to look right now is just at a single turn. So assume I have just one piece of wire that's in a loop like this. So we call this a current carrying. It's a current carrying loop, but it's a circular loop. So what each little segment of the wire is going to have a magnetic field around it that's circular. And all those little circular things are going to kind of add together so that the center of the loop, the magnetic field is going to be larger than if you just had a straight piece of wire. It's kind of putting them all together. And again, I'm not sure if, let's see if I remember when you calculate the formula for this. So I'm looking for the magnetic field inside a current carrying loop, circular loop, yeah. Let's see how they do that. I actually use calculus. Using trig substitution, so we haven't gotten that far yet. We may come back and do the calculus for this thing. But actually, you don't use Ampere's law, you use calculus to do it. And, well, yeah, you do use Ampere's law. It's just, it's a little more complicated. So I'm just going to tell you the result. So the magnetic field on the axis, that means right at the center. So let's draw, here's my loop. Okay, so that's this thing. And the question is, what is the magnetic field right here, right at the center? And let's say the loop has a radius of capital R. And there's a magnetic field strength, there's a current. So it's not surprising if this thing looks very similar to what I just have here. It turns out the magnetic field at the center of the current carrying loop is equal to mu0 times I divided by 2R. So the only thing that's different is you don't have the pi in there. But it's basically around each wire you're going to have these loops. They're going to keep going looping around, and the radius of the hoop, so if you took one out to the radius here, you'd have a certain distance from the wire to the center, and you would have a magnetic field value, and then you add all those things together, and it turns out to be that. So to increase the magnetic field, we could make the radius smaller, or we could increase the current, basically. Those are the two options. Now, if you have more than one loop, so I'll say that's for a single loop. So move this down a little bit. So we'll say for multiple loops, the magnetic field is mu0 I times n divided by 2r, where n is the number of loops. So that's why they've got 200 loops here, because we want to generate a magnetic field strong enough that we can measure it. If I just had one loop, it would just be so small that it'd be very difficult to measure the magnetic field. We have these nice magnetic field sensors too, so we're able to measure magnetic field pretty good. And what you're going to have basically is, right at the middle, it's going to either be pointing this way, straight this way, or straight that way because of symmetry. If you're over here, it's going to be pointing again, it's either going to be pointing down or up. If you go somewhere in here, it's going to be somewhere between the two. So it's a little, if you wanted to figure out what the three-dimensional magnetic field was around this loop, it's fairly complicated. But to find it right in the middle is pretty, it's a fairly simple equation. Is it a maximum in the middle? We'll find out when we try our experiment next week. Because if you move closer here, you should be closer to these wires. So as you get closer, the magnetic field should increase. And then maybe it decreases out here, but then it increases back to some value in the middle, maybe. I don't know. And then the final thing is this scenario, which these are called solenoids. And so instead of the wire being essentially at one X location, it's spread over a larger X location. It's wrapped in so it basically starts here and then they just wrap it around. And one thing you'll notice, so here's one that goes inside the other, and this one has much heavier wire. So this has fewer loops. This one has more loops, but the wire's smaller. If you use the same wire here, then this one's going to have a lot more current. If you put a certain voltage across these terminals, the current through this thing is going to be a lot higher because the wire's fatter, the resistance is less, and here the resistance is more because the wire's small. But they're all wrapped in plastic. Each wire has to be separated electrically from its neighbor. So I'm going to hand those around. You can look at those solenoids. You can go, ooh, look at that. So again, there's you actually can use Ampere's law to come up with the equation for the magnetic field inside a solenoid, and it turns out that the magnetic field inside a solenoid, an ideal solenoid, is the same anywhere inside. So it's inside there's a constant magnetic field, whereas in the case of this loop, the magnetic field strength here is different than there. But with that, when the diameter of the loop is small compared to the length of the loop, it's pretty constant inside, and then as it comes out. And so if you look at the magnetic field on a solenoid versus a magnetic field around a bar magnet, they look very similar to each other. So I'll demonstrate that in a second. Not actual with real stuff, just showing you how it works. Okay, so here's my solenoid. It's going to have some radius, it's going to have some length. It's going to have all these wires looped around it like this. So the dimensions of the solenoid, you'd have the radius of the solenoid, and you'd have the length of the solenoid. Call it L. You could also have N, which is like the previous one, the number of loops. You could also have small n, which is number of loops per length. Okay, so again, I don't remember what the exact formula is, so I'm going to look for solenoid. Oh, there we go. Applications of Ampere's law. Okay, there it is, what I'm looking for. So let me add a page. So it turns out the magnetic field strength inside a solenoid is equal to mu zero, there's our little friend mu zero, N times I. So it turns out that L doesn't come into play except in calculating small n. So I guess you could say it's also equal to mu zero times N times I divided by L. Same thing. So let's define everything again. So this is magnetic field strength in Tesla. That's inside. Mu zero is the constant. Let's see if I have it in the book here. Mu zero. It's called well, they call it the magnetic constant. But anyway, it's 4 pi times 10 to the minus 7th. It's interesting. The book has WB/A times M. I'll explain that in a second. N, we already defined, number of loops. So I don't need to define the rest. I already have those defined. L is the length of the solenoid. In meters. So the WB is a Weber. And what that is, Tesla per meter squared. So this Weber thing is, we call it magnetic flux. So it's just, well, yeah, it's how much magnetic field you have per given area. So the larger your magnetic flux is, the more concentrated the magnetic field is around a certain area. So, stronger magnets are going to have higher magnetic fluxes. But you could substitute it in. If you put in Webers, you get Teslas per meter squared, or is it Tesla meter squared? Actually, I think it's Tesla meter squared. Let me fix that. I'll explain why I know that. Again, it has to do with the units. Tesla meter squared, because it's actually the magnetic field times the area. And the reason I knew I was wrong, because if I went up here and I put in Tesla per meter squared, I'd have meters cubed, and I knew that wasn't going to work out right. So again, to make a solenoid, to get the highest magnetic field in a solenoid, you want to increase the current, increase the number of loops per length, and that's it. Because it's just, what is it? Where's the formula? I already lost it. It's up there. It's hidden. mu0 times n times I. So it's just the number of loops per length times the current. Okay, we're not taking a break, but I'm going to show you a video, another video. Narrated by Steve Nicholson. So this is just going back to talking about how a DC motor works. So let's just stop on this slide and explain what's going on. So what we have is two permanent magnets, and the magnetic field lines are, without this wire in the middle, you just have straight lines. But with the presence of the current carrying wire, you get a magnetic field around the wire, which interacts with the permanent magnetic field, and that causes the wire to want to be pushed up. Okay, so that's just the concept of force on a current carrying conductor, but also how it warps the magnetic field. Okay. I don't know what he's saying, but okay. Now here's the motor. It's kind of like the one I made in class. So I'll get to a point. Okay. So what you have is a battery, and then you come in with the wire to this thing. And so these are the contacts that I had. And then if you remember, when I handed around the armature, it had copper. So you had copper contacts, and the shaft was copper. So you have physical contact here, which allows the current, the electrons to flow through from here to the stationary, to the moving part of the motor. And you have this split ring. So what happens in this case is the current goes, if you flip the switch, the current will go through this wire into this half of the armature up to the wire, and then the current will flow through the wire, and because of the force on a current carrying conductor, there will be a force. Actually, the force will end up being both here and here. Well, there'll be a force here, but the force here will be into the board, so that way, and this one will be towards us. And they don't create any torque. But so let me continue on, because I'll show that in a second. So you got the magnetic field, and right now the loop is parallel to the thing is called a commutator, not a communist. So so there he's pointing at the battery. He's closed the switch. The current flows through the wire. Okay, so what's going to happen is the current's going to flow through the wire. The magnetic field is in this direction. The current is going to be in that direction. And so the force is going to be perpendicular to both of them, which is going to be, in that case, vertical. So it's going to be upwards, like same direction as the letter, going up that way. Whereas over here, the current's flowing this direction instead of that direction, and so the force is down, and so this force up and that force down creates a torque. So that starts the motor moving. But when it gets to where it's vertical, then the two forces that are associated with these parts of the circuit are both to be in the same direction, and you wouldn't have any torque. So you have to switch the order of current. And so somewhere along here, let's see where, let me see if I can, okay, so there's the current moving through different directions. Okay, there's also a left-hand rule, which is basically the right-hand rule, except with using your left hand. Okay, so what he's saying here is that with the magnetic field going this way and the current going that way, that the force goes in that direction. Okay. So that gives you a torque, and there's the equation. The torque on a current carrying loop is the magnetic field strength times the current. In this case, the length times the width, which is the area, times the cosine of the angle. At this point, you have no torque. The actual force would be in this direction on this side and this direction on that side. Okay. So let's move on. Let's move along here. Moving along. Oh, there's his hand again. And yeah, more right-hand rule stuff. But what will happen is, let me just explain how this commutator thing works, is when it comes around 180 degrees, then the current flow direction changes, and therefore all of the forces change in direction and cause it to want to keep rotating. Otherwise it wouldn't rotate. Without the commutator, it wouldn't be a motor. That's the basic concept, just by changing the direction. So you can, let me just, yep.
How would you limit the revolutions?
Yeah, why doesn't it just keep going faster and faster and faster? Okay, so that's a very good point. So, and we have to actually, it's in the next section of the book, but I'll try to explain it now. So yeah, why doesn't it just keep going faster? Well, for one thing, obviously, if you had friction, it would get really hot and you don't want it to, so, but there is a limiting speed that the motors will go. And what happens is that electric generator is the same as electric motor, except instead of it spinning something, you're spinning the motor. So it's you basically have the same arrangement as the motor, but you're on the end spinning it, and if you looked at the output of the terminals, you would see the current would be varying. It'll actually look kind of like this, which we'll find out why later. But also what it does is it as the current carrying loop spins in the magnetic field, it actually generates a voltage itself, which is in the opposite direction that the voltage that you apply to it. So as it spins faster, the actual net voltage, kind of like the capacitor when you put the dielectric material in there. You know, you had the electric field, which was in one direction, and the dielectric material aligned itself to oppose the electric field to give you a smaller electric field. So what's happening here is that the spinning motor, the spinning armature inside the magnetic field actually generates a voltage in opposite to the voltage, so the net voltage across the motor decreases as it speeds up, and there is some point where the friction or the load on the motor is balanced by the torque provided by the net voltage applied to it. It's called back EMF, but that's, so we'll talk about that again, but it's just to answer your question, yeah, why doesn't it keep getting faster and faster? That's a good observation. Okay, so that's a DC motor. So we'll skip that. Okay, so what are we doing now? Talked about Ampere's law, talked about motors, magnetic fields. Oh, I know what we're going to do next. Okay. So that's pretty much it. We've talked about how a moving charge creates a magnetic field around itself, and that magnetic field interacts with an external magnetic field to push things in certain directions, whether it's a charge or whether it's a wire or two wires. We've also talked about how do you quantify the magnetic field created by moving charges. The only one we haven't looked at is what is the magnetic field created by a single magnetic single charge particle. We talked about what the force was, but we didn't, what is the magnetic field around that little charged particle as it's moving? And we don't answer that question. It's too complicated. It's this moving magnetic field in space. Okay, but we did talk about the magnetic field around a wire inside a loop like this, right in the middle, inside a solenoid. Now, and we also talked about three laws, which were Gauss's law, which we said was that the electric flux was equal to the charge divided by epsilon 0, and we had Ampere's law, which said that the strength of the magnetic field, well, no, it said that if you integrate around then this is a line integral, not an area integral. So you integrate around the line of the dot product of the magnetic field and the distance vector around that loop. That's equal to mu 0 times I. Okay, that was Ampere's law. Okay, so here's another guy, Faraday's law. So Faraday was an English guy, and I don't think he was actually he wasn't like a professor. He was just some guy who who's a genius, but did more practical stuff. And he thought, if a moving charge created a magnetic field, then could a magnetic field create a moving charge? So is there any way that you could was there any way that you could make charges move, specifically in a wire, by doing something with the magnetic field? So he came up with this experiment, which turned out not to work, but it led to something that did work. So what he did was he had a wire, and he had a loop like a solenoid. And then he took this over here, and he had a battery. So here's your battery. He didn't have he had a much simpler battery. And then over here, he had another loop of wire in close proximity. He might have even had a little piece of metal that went through the whole thing to tie them together. I'm not sure if he did or not. And over here, there was a meter. So this meter was to measure current. So I'm going to say so we'll write that in there. So this is to measure current. And he thought if he ran current through this wire, so the current goes through the wire, you get this magnetic field, which was obviously occurring. So here, these are just my magnetic field lines. So we got this magnetic field going through the solenoid. And he thought that if I ran current through here, that magnetic field would create some kind of electrical current in this secondary loop. So he put this gauge there to see if he could measure anything. So he hooked up the battery, and nothing happened. Okay, so the magnetic field was not making anything happen. So, but what he did notice was that every time he opened and closed the switch, let me try this experiment again. So I have a switch here. So here's the switch. When the switch is closed, nothing's happening. When the switch is open, nothing happens. When the switch is closed, nothing happened. But if you plotted voltage, and he didn't plot it because he didn't have any means to do it, but if you measured current, let's say you're measuring current over here, and here's time, every time he'd flip the switch, it would go like this. And then when he opened the switch, it would go like that. And of course, he tried it again, and when he closed the switch, it went like that. When he opened the switch, it went like that for a real short period of time. So all he saw was just like the arrow just went. So he's trying to figure out what's going on. So he came up with this law, Faraday's law. And what it says is that basically the voltage, he called it EMF, is equal to negative some constant, we'll call it K, times the change in, I'm going to use this phi again, but I'm going to put a little b here. Okay, so it's d phi sub b dt. So I'm going to write it out. Okay, so Faraday said that the voltage generated in a loop of wire was proportional. That's where there's the K there, proportional to the rate of change of the magnetic flux. And the magnetic flux, this phi sub b, is just equal to the magnetic field times the area. So it's just like water flowing through a pipe. This is kind of like the pressure. That's the area, or velocity, I guess, in the area. So that's the magnetic flux, phi sub b. It's just so if you have d phi sub b dt, that's what he's talking about. So Faraday's law says it's the rate of change of the flux with respect to time. How can you do that? Well, you can have the magnetic flux change, the magnitude of the magnetic field, or you could change the area somehow or another. So both of those will change the flux. And I'm going to use this as my example. So here's a loop of wire. And let's say we have a magnetic field. Hey, I just happen to have a magnet. How about that? So I've got a magnet, and see if I can do it without breaking it apart any further. So see, it's already broken, I think. No, that's a notch. Okay. The notches tell you whether it's North Pole. Okay, so here's the magnet, and there are lines coming out of this, magnetic field lines coming out, and they go out and they come back around like that. Okay, so if I want to know what the magnetic flux through this loop is, I just take the magnetic field that you have to imagine, and right now there's a magnetic field. It's strong because I have the magnet, which has the strong magnetic field, right inside the loop. If I moved it over here, I still have the same area, but the magnet's way over here, so the magnetic field due to this magnet's small. So if I go from here to here, I'm changing the magnetic flux inside this loop is going to be changing. It's going from basically 0 over here to some maximum. So how can I make that how can I increase the change in magnetic flux? Well, one is I could put two magnets together. Okay, so here's two magnets that I put the same poles together, which is hard because they want to repel each other. But you know, this has twice the magnetic flux that this has. So I could put two magnets together and go at the same speed. Okay, so that would double the magnetic flux change because I have the same time involved, I have the same area involved, but I doubled the amount of magnetic field. So that was one way of doing it. The other way would be to take the same magnet, and instead of going like this, to go, to move faster. That increases the rate of change because I'm making the change faster. dt is smaller. The other way of changing the magnetic flux would be to take this area and rotate it around like that. So here the magnetic flux is maximum, and then here it's 0, because the area is in the wrong direction. The area is this way. So I could cause a change in magnetic flux doing it that way. So we're going to do that on Wednesday. Is we are going to hook up the interface. We're going to put a voltage sensors right here, and we're going to take this magnet and we're going to go, and you'll see a little spike in voltage that we can look at. And the interesting thing is that if the spike is positive here going in this way, coming out is negative. So it'll be positive, negative. Or if I went through, what would happen is it would be positive till this point, and then when I go out the other way, it's negative. So there's two ways of, I can either take it in like this and out, or I can go straight through, of course. And then if I bring it back before, so what will happen is you'll see as this thing goes in, it'll go, and then just as it goes out, it'll go like that, and then back over like that, which is pretty cool. Or you'll see that I can increase the voltage spike by sticking the two magnets together. So do the same thing, because you can only do it so fast. How fast can you do it without hurting yourself, throwing your shoulder out of joint or something like that? So now the third way we're not going to do, because it's hard to go like, I guess you could do that, but that's actually how electric generators work. You have a loop of wire, and you have a magnetic field which you impose by having a permanent magnet. So if I had a permanent magnet here, a north pole and the south pole here, and then I had some way of rotating this thing around, what you would find out is that and measure the voltage in this loop, it would actually be a sine wave. You generate an AC voltage by having a fixed magnetic field and rotating this thing around. Well, hey, that's kind of like a motor, except when we had a motor, we stuck this inside the magnetic field, sent a current through, that causes it to rotate. In the case of a generator, we're the one that we're putting the input, we're rotating it, and what we're getting out is the current, and that's what we do to make all of our great power. Just got to find out different ways to rotate it. You can run it by an internal combustion engine, you can do it by water turbines, by using wind turbines. All of those things are using Faraday's law that says the voltage generated in a loop is equal to some constant times the rate of change of the magnetic flux with respect to time. And without that, we would be still riding horses. And well, maybe we could have cars. Maybe, we could still have cars, but we wouldn't have power in our houses or anything like that. So that's pretty cool. Okay, what else am I going to tell you? So it turned out, this is a previews of coming attractions. There was this guy named Maxwell, James Clerk. Why do I include his middle name? Because I think it's weird. Clerk Maxwell. He was an English guy too. And what he did was he came up with these, he used Gauss's law, Ampere's law, Faraday's law, and another law. It's like 4 laws. And what basically he was able to do was mathematically relate magnetism to electricity. Up to this point, we had all these separate experiments that people did, and they came up with these laws, but there was some feeling there was some connection between electricity and magnetism. But he came up with a mathematical basis, which is pretty impressive. I'm going to show you Maxwell's equation. It's not that you're going to understand it, but hopefully you'll look at it and say, man, that is impressive. Okay, so let's we'll look on Wikipedia. Maxwell's laws, equations. Okay, Maxwell's equations. I guess they're not laws. And so yeah, relates electricity and magnetism. And yeah, here they are. So there's Gauss's law. So, it's not as simple as what I showed you, but the E dot ds, that's the electric flux, is equal to the integral 1 over epsilon 0. So there's epsilon 0. And this is charge per unit volume times volume. So they're basically saying add all the charges together. So it is actually Gauss's law. It's just in an integral form. Then you've got Gauss's law for magnetism, which says, so that thing, that fancy looking thing, is what you call a area integral. So this is a line integral. This is an area integral. So and I think we had one up here too. This should, whoops. Yeah, you can notice this is an area integral. And this is the differential area. So S is the surface area. So basically what you're doing is you're taking the electric flux dotted with the surface area, little surface area, ds, and you're adding all those up around the area. And you can do the same thing with magnetic. So if you take the magnetic field vector dotted with this area vector over the area, those add up to 0, not to this. And I was just thinking about this is, one thing I said was that with electric charges, you've got a positive charge and you've got a negative charge. Clearly defined opposites. With a magnetic field, you don't have clearly defined opposites. You've just got a direction. And that's why they look similar but not the same. The reason you have a right-hand side is because we have positive and negative charges. The reason we don't have anything on the right-hand side here is because we don't have positive or negative poles by themselves. Okay, so that's kind of an interesting math. I hadn't thought about that before, but that's the good thing about teaching something. A lot of times you have these moments of, oh my. Okay, then you have Maxwell and Faraday's equation. So this is Faraday's equation. This is basically the current. So if in a wire, that term would represent the current. Actually, also, it would have mu 0 in there, or epsilon 0, mu 0. Yeah. And then this is this integral. Actually, this is a rate of change. So that's it's a little bit different than Ampere's law. Looks like Ampere's law, but involving some kind of derivative thing. And then the last one, oh yeah, so there's Faraday's law. This is Faraday's. I got confused. So this is Faraday's law. We just looked at that. So let's just look at the simple version of it. The simple version was that where did I go with that? Yeah, I said that lost my equation here. Gauss's law. Where did I end up there? I don't know. I got backwards. Maybe is it down here? Oh, here it is. Faraday's law. Voltage is equal to some constant times the rate of change of the magnetic flux. Okay. So I'm going over here. So this is the magnetic flux. So this is the rate of change of the magnetic flux. And that equals this, which actually is related to the voltage. So that's Faraday's law. And then you have Ampere's law, which is much more complicated than what we're used to dealing with. So Ampere's law that we looked at said the line integral of the magnetic field vector dotted with the ds. So that part's exactly the same. The right-hand side is not just mu 0 times I. It's this more complicated, crazy stuff. But it simplifies down to this equation somewhere here. Yeah. So those are the law. You have Gauss's law. You have Maxwell's law, kind of like Maxwell's version of Gauss, the magnetic field version of Gauss's law. You've got Faraday's law, and you've got Ampere's law. Okay, so you got all those four things, and he did it mathematically. And the impressive thing was that Maxwell said, well, based on all this math, that if we have a rate of change, if we have this, not only do we have, if we have this moving charge at a certain velocity, if we actually accelerate the moving charge, so we have this charge that's in a piece of wire, and it's moving from one side to the other, so it's going like this. It's not only, it goes from positive velocity to negative velocity, and it actually goes from 0 to the maximum, and then to 0, and then to maximum the opposite direction, then to 0. So it's like a spring oscillating. So you can imagine this electric charge oscillating in a wire, and what you have there is you have an accelerating charge. So here's a stationary charge. Here's a moving charge, but I'm moving at a constant speed. The third case is you have a charge which goes ding, 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 like that. And he predicted that if you have a moving charge going like this, that you should generate electromagnetic waves. And he predicted that the speed of an electromagnetic wave, based on just mathematics and his equations, would be 3.0 times 10 to the 8th meters per second. That had not been measured. And then this other guy named Hertz actually measured the speed of electromagnetic waves to be 3.0 times 10 to the 8th meters per second. It was exactly, his mathematical calculation of the speed of electromagnetic waves, which are light, sound, not sound, radio waves, microwaves, X-rays, infrared rays, all of these different kinds of electromagnetic waves all travel at the same speed in a vacuum, which is 3 times 10 to the 8th. So that's impressive. Again, this is when people didn't have computers, just using their big brains. So okay, so that's kind of the general overview of chapters 19 and 20. Okay, so I'll forget where I am on assigning homework. So I think we can assign chapter 20 now. We will really, the next thing, the only thing we have left to talk about is AC circuits and inductors and electromagnetic waves. So that's the remaining things that we have to say. So give me 3 more minutes. I really have 7 minutes, but I'm going to give you a break here. So if I, when we were using that circuit thing to make electric circuits the other day on the computer, there were three main things we had. We had resistors, we had capacitors, which we've talked about, and the third electrical element we have is what's called an inductor. And who's got my coils? You got it? Did it come up to the top? Can you hand it back down to me wherever it is? Oh, okay. So.
What do you want us to turn in chapter 19? Because it wasn't assigned.
Oh, it wasn't assigned yet? Well, I'm assigning that too. So let's. We don't have class next Friday, so we'll say 19 is due the Monday after next. Okay, and then chapter 20 will make due Wednesday after that, because you have your calculus test, so you'll have plenty of time to work on your physics stuff once we get through the calculus test. So it's Monday and Wednesday of not next week, but the following week. So if you look at that inductor, that's the symbol for an inductor. Kind of looks like this, right? Which it is, okay? So the third major element of electric circuits are inductors, and they're basically solenoids. Now what we said was that if you run a constant current through this wire, you're going to create a magnetic field. But what really happens is you start with zero current and you go to a maximum current and then you come back down to zero and then you go the opposite direction. So when an inductor is used in the circuit, it's when things are changing a lot. And it turns out, so I know I'm already past my time, but here we had Ohm's law that said the current was equal to voltage times there's resistance. For a capacitor, we said that the charge was equal to the voltage times the capacitance. And it turns out that for this electrical element, that the voltage is equal to a constant, which we'll use L, times the rate of change of the current with respect to time. So this is voltage. This is what we call inductance. And this is just the rate of change of current. So it's the additional relationship. The other two relationships are linear relationships for resistance between current and voltage, for conductance between voltage and charge. For an inductor, it involves the rate of change of the current. So what this says is when you change the current, when the actual current is changing in this loop, going from zero to some value, the amount of voltage that's generated across this element is proportional to the rate of change of current instead of equal to the current. For resistance, it's the opposite kind of situation. Here it relates to how fast things change. And so it turns out that inductors in your circuit are another way of slowing things down. Circuits don't like to go from 0 to 60 in 0 seconds. They like to go slower, and these things tend to slow things down in the circuit. They're also used for like oscillating circuits. So if you're trying to create oscillations like a radio, if you've got an old radio station, you'd have to use these to generate your sine waves to send. Okay, so that's it for today. I know there's a lot of material to absorb, so